Let me introduce Pablo Soberon, who will speak about Tverberg problems. So I hope it's a very interesting problem related to Tverberg's theorem, and these kind of results are very interesting. And for some, say, fault maps of related to some prime numbers. And in this talk, Pablo will speak about new results that not related to the prime power.
Okay, well, thank you. Thank you everyone for being here. It's nice to see so many friendly faces and be able to talk about this relatively recent result that I worked with Florian Frick. And so hopefully by the end of the talk, I can convince you that there's a theorem and an idea of the proof. And yeah, tell you a bit about how this came about. Now, I did like the introduction saying that I would talk about Tverberg type problems because I did have a bit of a warm-up before talking about the topological Tverberg theorem. And so for this, what I want to think about is, just to set the mood for Tverberg type problems, to think about the following set of points in the plane. So I have 8 points on the plane, and usually in Tverberg theorem, you want to split them into pieces where the convex hulls intersect. But here I'm going to do something different. I want to divide them into pairs of points. So I'll just draw the edges between each pair I constructed. And now we usually want things to be intersecting. Now my edges are clearly not sharing a single point. But instead of drawing edges, what I'll do is I'll start drawing disks. So for this edge here, what I'll do is I'll draw the disk whose diameter is that segment, okay? And I'll do the same thing for the second and the third and the fourth one. So I get a set of 4 disks, and you can see that there's a region here that they all share in common, okay? So this is what I would call sort of a Tverberg for disks in the plane. And this is a actually very recent result by Homer, Perez-Lantero, Seara, and Silveira. And they show that if you give me an even number of points in the plane, then I can always find such a perfect matching. I can split them into pairs so that the disks induced by them share a point in common. Okay, I'm thinking about the closed disks induced by whose diameters are the pairs I have here. But actually, they prove something much stronger. They prove it with n blue points and n red points, and the matching they get is a red-blue matching. Sort of like a colorful Tverberg theorem. And you can do a bit more. So I can, you have here a matching. I can add some edges. You can now see that this is actually Hamiltonian path. And if I do this, now I won't do it one by one, but I draw I have 8 points. So I have 7 edges here. I draw the 7 disks, then they all share a point in common. And this is relatively recent work with a student that worked with me over the summer. So I don't only get a perfect matching, I get a Hamiltonian path with this property. And within a Hamiltonian path, if I just take the first edge, the third edge, the fifth edge, and so on, the odd ones, that makes a perfect matching. So you recover the previous result here. And if I give you an odd number of points, say I give you now 9 points here, I can do something similar, but instead of doing a Hamiltonian path, I'm doing a Hamiltonian cycle. So I get sort of ideally 1 more edge here. And so with 2n plus 1 points, we can get a Hamiltonian cycle here. But this sort of problems, everything I told you was in the plane, but there's no reason why they wouldn't work in high dimensions. So if this is a type of problem you like, and you get bored of what I'm talking about here, you're welcome to start thinking about this sort of things. I actually don't even know if the Hamiltonian cycles should also work with an even number of points. I suspect it is. Even the perfect matching is not known in dimension 3 or higher. So this Tverberg type theorems for disks is something I find interesting. Okay, so that was a warm-up. Now let's go back to the main topic about the topological Tverberg theorem beyond the prime powers. And so this is joint work with Florian. This is a picture from a conference about a year ago in Oaxaca, which is when we started thinking about this problem. The guy in the middle, that's Pablo Blagojevic, this is Florian. And the main idea for what I'll tell you is we basically got it in that conference, and then figuring out the details was what took quite a few months to make it work precisely. Okay, so what I want to convince you is that the main idea is simple, and then tell you a bit about where the details can start getting murky, but they end up working nice. So let's go back to a bit of history of the subject. Again, 9 points on the plane. I give you any 9 points on the plane. You can always find an extra point here and divide the 9 points into 3 triangles, each of which surrounds this point here. And this is not something that's special about this 9 points or the fact that it's precisely 9 points, just any number of points which is a multiple of 3. So I give you 3 Q points on the plane. You can split them into Q cycles, Q triangles that surround a common point on the plane. And this is Birch. He proved it in the 50s as an undergraduate. And you can rewrite this. So whenever I see triangles, I like to fill them, just making them into convex sets. And you can write then this as given 3 Q points, you can split them into Q sets whose convex halves intersect. And once you write it this way, then you might notice, what if I drop these 2 points here? Then this triangle would just leave me with this edge. This triangle would just leave me with this edge. And the convex halves still intersect. I just have to change my red point here to this one, right? So actually, Birch noticed that you could even save 2 points here. And it's not about which 2 points I erased, but any 3Q minus 2 points in the plane can be split into Q sets whose convex halves intersect. And unlike the warm-up, for this particular theorem, we do have a high-dimensional version, which is Tverberg theorem. Given Q times D plus 1 minus D points, in RD, they can be split into Q sets whose convex halves intersect. Sometimes you see this particular number written slightly differently. But this is Q times D plus 1 is the number of vertices I would need to do Q simplices. And this is sort of the number of points I could save because life is good and we could save those points, okay? And since we'll talk about this, let's just do a slightly different example. Now with Q equals to 2, it's not the most interesting case, but this is so Radon's lemma. And in the plane, it's telling me if I give you 4 points in the plane, you can split them into 2 sets whose convex halves intersect. This is 2 times 3 minus 2, so that's 4 points, right? And they can either look a partition into 2 sets, 3 and 1, or 2 and 2. 3 and 1 basically means you have a set which is a triangle containing the other one, and 2 and 2, 2 segments which intersect. Now this drawing is perhaps not the most exciting thing to look at, so let's just make it a bit prettier. And then it looks like I'm trying to draw a tetrahedron, right? This looks like I draw the tetrahedron and one vertex was behind one of the faces I was drawing. And as I move it around, this vertex which is behind might pop up on one side, it pops onto this side, and that's when I get this partition like this, okay? So again, another way of looking at this is there's essentially 2 ways of drawing a tetrahedron on the plane, and they satisfy this convex hull intersection property. So for any drawing of my tetrahedron, the three-dimensional simplex, to the plane, there are two vertex disjoint faces of the tetrahedron whose images intersect. And here I have a linear map so that everything is nice and straight. Okay. Now, if you want to talk about Tverberg's theorem, then you can write it the same way. Now, this q minus 1 times d plus 1, remember that a simplex of this dimension has one more vertex. So it's telling me that a linear map from this high-dimensional simplex to this low-dimensional space, you can find q vertex disjoint faces whose images intersect. And the key thing here is we get this for linear maps, right? So the question that quickly popped up, or the following, Imre Barin asked this question 10 years later, 10 years after Tverberg proved his theorem, where is this really something that follows from the linear structure you have, from the fact that the map is an affine map or a linear map, or is it for any continuous map? Is it actually a topological statement, and then the fact that affine maps are continuous just gives it to you for free? Okay, so you get this conjecture, which is what we know as a topological Tverberg conjecture, and so it looks a bit like this, right? So you let your inner Salvador Dali out, and you draw this simplices being wiggly, and you want to see if you still get intersections as before. So you get this conjecture. The first case, when q is equal to 2, was proven just 3 years later by Portmoshki and Barin, and it basically just uses, I think, Boursoukula. Shortly after that, Barin, Schlossman, and Schuck, they proved it for the case when q is a prime number, using slightly more advanced topological techniques. And then again, with a bit more topology, so in 1987, he proved this for q a prime power, which was an unpublished preprint. I think the first published proof was by Volovikov in 1996. And so there was this feeling in the community that, okay, this worked for q equals 2, for q equals a prime, for q equals a prime power. Every time the reason you couldn't get past this was because the techniques you were using, they really broke down, but they didn't mean that the theorem itself broke down, right? So after 1987, there's basically silence on this conjecture. I wouldn't call it radio silence because there are different variations of Tverberg for which there were advances and new results on this. But as you can prove the conjecture, you start looking for someone to blame. And the first idea is, okay, it's topology. It's because we haven't found the right tools to actually prove this type of results. And the big surprise actually comes in 2015 with the counterexamples for the topological Tverberg conjecture, that if q is not a prime power, then you start getting counterexamples for this. So it's not actually the fault of the topological tools we were using. The conjecture was actually missing something. So you might want to shift the blame a bit, maybe blame the person who found the counterexamples. Then it's also fair to blame Isaac Mabillard and Uli Wagner, because the construction by Florian was based on what they called the Orfold-Whitney trick, in which they could get some interesting properties about Orfold intersections of continuous maps of a simplicial complex toward D. And ultimately, it's basically that the conjecture was false. So we I mean, you can't prove the conjecture by Barin, but maybe you can not give up completely on this problem and see, okay, what needs to be tweaked for us to get a very good topological Tverberg theorem. So maybe this was a bit too ambitious in the number of vertices you actually needed here. And I should mention that even though Florian found those counterexamples with this number of vertices, there have been improved constructions with a bit more vertices here by Avakumov, Korosev, and Skopenkov. I think that's the current record holders for lower bounds on this problem. But let's go back to the 9 points I drew at the beginning, okay? So the reason why 9 points are interesting in the plane, if I want to divide them into 3 pieces, is because that's when I would expect the intersection to be full dimensional, okay? If I did it with 7 points, the intersection, I would expect it to be just a point or 0 dimensional. If I do it with 8 points, if I say remove this point, then the intersection would be the segment. I should expect it to be 1 dimension, okay? So when I get q times d plus 1 vertices, that's when I expect the intersection to be, and I want to divide them into q pieces, then that's when I can expect full dimensional intersections here. So Blagojevich, Frick, and Ziegler, they conjectured that for any continuous map now with this many vertices, with this dimension, so the number of vertices is this plus 1, q times d plus 1 is the number of vertices I actually want. There are q vertices joint faces whose images intersect. So this is their attempt to save this topological conjecture by improper. And the main result I want to tell you about today, so again, it's like this old result by Birch, but now topological. For the rest of the talk, my drawings will be completely affine because it's easier to make them. So this is the last weekly drawing I'll have. But this is now what we were able to confirm, that with this many vertices, then you get a topological Tverberg. Okay, so the problem of finding the optimal numbers is between this and the current record for the lower bound. Okay, so hopefully I can convince you. So I'll tell you a bit about the ideas behind the proof of something like this, and where exactly the details with your slide. Any questions so far? It's good. Okay. So before I do this, let me tell you about how one can try to prove a version of this, not in general, but a simpler version, which is when q plus 1 is a prime power. Okay, so this should work for any value of q. But a very nice trick, I'll call it the German trick because most of the people I've seen using it are either Germans or have been living in Germany for quite some time. And the idea is if you have a problem of this type, you add 1 point and then you ignore it, okay? So how does a trick like this actually work? Well, suppose q plus 1 is a prime power, and I want to prove this result I told you about. So I give you q times d plus 1 points. I want to split them into q pieces whose images intersect. So I'm always thinking that I have this function from the high dimensional simplex to RD. So here I have 18 points in the plane. So q should be 6. I should find 6 triangles who intersect, or weakly triangles if I have this map in the mind. Okay, so these are the images of the vertices only. And so I add 1 point. And so this is my new number of points I have here. And this number of points I can, so with the plus 1, I can write it this way, q plus 1 minus 1 times c plus 1 plus 1. And if you recognize this, this is the number of points Tverberg would want to split into q plus 1 pieces. And the map I had from my 17-dimensional simplex to RD, I can extend it to an 18-dimensional, to a map from an 18-dimensional simplex, where this is the image of my new point. And so Tverberg, the topological Tverberg theorem tells me, okay, since q plus 1 was a prime power, I can find the 7 pieces whose images intersect. And there's actually at most one of the pieces that contains the extra point I drew here. So I can just remove this face. I had q plus 1 faces, q plus 1 sets, so I'm left with q sets and this extra points here. And that actually gives me the sets that I wanted. I get q sets whose come from pairwise disjoint faces whose images intersect here. If you want to really get triangles, you have 2 segments here, and you can add this point to one of the segments and this point to one of the segments, and you'll have your 6 triangles intersect, okay? And actually, this trick of adding 1 point and ignoring it, for example, for the warm-up I told you about, the way the result for an even number of points with a Hamiltonian path and the odd number of points with a Hamiltonian cycle relate to each other is precisely by this trick. If I give you an even number of points, you can add 1 point, find a Hamiltonian cycle, remove the extra point you added, and that gives you a Hamiltonian path for the even points you started with. So whenever you can apply this trick, it usually gives you very nice results. We also have a simple proof of this result for the case when 2q plus 1 is a prime number. But ultimately, we need something new for the moment when q just doesn't have any nice number theory properties. So how do we prove the general case is the big question here. Let me go back to how do we prove a standard Tverberg type result, say when q is a prime power, and or let's do when q is a prime number, where we get even fewer topological requirements, and we can see exactly how things fall down. Okay, so how do we? If I give you 9 points of the plane, how do I find 3 pieces whose images intersect? So what I'll do is I assign to each point I was given, or vertex in my original simplex, a label from 1 to q. And then what I do is I take the image of the points with a 1 assigned to them, the points with 2 assigned to them, the points with 3 assigned to them. And what I have is to find an assignment so that these points have a point in common, okay? So what I want to do is to parameterize all the possible ways of assigning a label. That would be the direct product of q with itself, with this set with itself n times if I was given n vertices, but I'll do it with a topological join because it allows me to parameterize not only the partitions, but the partitions with a point selected in each of them. So a point in the face with 1, a point with a face with 2, a point in the face with 3. I'll go a bit more into details about this. So if I have this point P1, P2, P3 parameterized by this set, it sort of gives me a function from this set to, in this case, it would be or to the d q times. I have a d plus 1 for technical reasons, but it constructs a function, and it's basically what I want to know is for this triple P1, P2, P3, is it the case that they get to be equal at some point for some x? So I have a map from the parameterization of all possible partitions with the points P1, P2, P3 to a low dimensional real space, and I'm asking, do I intersect the diagonal of points that look this way? So now it's a statement about maps from this set to this set, and I want to say something about their image, okay? It starts looking more and more topological, so let's just go through a bit how this is done precisely. So I'm going to make a matrix of points with one row for each of the vertices I started with, so I should have 9 rows here, and one column from the number from 1 to q. So the numbers here go 1, 2, 3 up to q, and that's for each of the rows I'll have here. Okay. So if I choose 1 point from each row, this is like assigning my vertices, right? A number from 1 to q. So if I take an abstract convex combination of those, so for example, if I took these points here, it means that vertex 1 and vertex 4 were in the piece that was assigned label 1. If I have an abstract convex combination of these points, I can look at the sum of the coefficients assigned to points here, which is lambda 1. And the combination of the points here, maybe since the coefficients add to lambda 1, I can write it as lambda 1 times x1, where x1 is now a convex combination of the points in this column. Okay? So the way this configuration space is the n-fold join of this space. And so what I'm going to record is lambda 1 and then lambda f of x1. So I record this x1, and I construct this f of x1. If lambda1 was 0, then here I just record 0, and that's perfectly fine. And I do this for each thing. Okay, so notice that this block here, it has one coordinate and then d coordinates, so that's why I have the d plus 1, and I have this q times. So this is how you construct the function that I was telling you about. So you have this block here, and you have these q blocks. And the important thing here is that you have an action of the symmetric group on q elements. If I permute these columns, what I end up doing with their image is I permute the blocks here in the same way. So this gives me an equivariant function from this space to this space, and I want to know, okay, do I hit the main diagonal or not? Okay. And the last tool I'll need to guarantee that I do this is the following result by Dold, which is like a broad generalization of the Borsuk-Ulam theorem. If I give you two topological spaces with free actions of a group G, and I know that X is, I know the connectedness of X and I know the dimension of Y, then there exists no continuous equivariant map from here to here. Okay? And in this case, with what I had before, if I don't hit the main diagonal here, I can do a dimension reduction argument on the target space and then get a contradiction to Dold's theorem if I don't have the partition like I wanted. Okay. Now here it was very important to have free actions of my group, meaning that I have to say something interesting about the fixed points of this map. And this is why for this particular technique, I needed Q to be a prime number so that the actions of this permutation actually look nice. Okay, I actually use ZQ instead of the whole symmetric group, and it makes my life a bit easier. So this is the sort of the proofs that we had in the 80s. They work really nicely. This theorem by Dold is actually quite nice. And the surprising thing about our result is that as far as how much topology you need, it's just this result by Dold. We can't get it with just Dold's theorem, okay? And so in terms of the connectedness, if you're not familiar with the joints, if Q is equal to 2, then this set, I think of it as a discrete set of 2 points. If I join it with itself, it's a circle. If I join it with itself, it's a sphere. And so the connectedness actually starts growing as you increase this, right? So this set is highly connected. And that's basically also what allows us to deal with this. Okay, so let's go back to our 9 points and think of how we could prove this. What's the main change with what we're going to do if Q is not a prime number? And so I'm going to create I'm going to consider a prime number P, which is an artificial parameter, and I'm going to think of it as a very large prime number, which is much larger than Q. And instead of assigning a label from 1 to P to each vertex, I'm going to assign to them a set of labels. Okay, so they should look, maybe P is 7 for our case. It looks a bit like this. And I can do again what I was doing before, taking this face with everything with a 1 in it, with a 2, 3, 4, 5, 6, and 7. 6 and 7, okay? And so now I have my 7 sets, which, my 7 faces, which I'm considering. Remember, I only want to extract 3 faces from here, okay? So if I'm lucky, 2 things will happen. The first one is all the 7 faces I consider, they will have a point in common. And among those 7 faces, I should be able to find 3 of them which are pairwise disjoint. Okay? So if both these things happen, then I get the point of intersection one way, and then I get the disjoint faces from the large set that I wanted. Just like in the warm-up, if I wanted a perfect matching and I found a Hamiltonian path, in that big structure, I find the one that I actually want. Okay? So it's the same story here. Now, the big question is, well, am I just assigning any set of labels? And the thing is, we'll be very careful, and I'll construct a simplicial complex sigma, and I'm only assigning sets which are faces of the simplicial complex. So what do I actually want from sigma? So the new configuration space will be the n-fold join of this sigma. And so we want first sigma to have a free action of ZP so that we don't run into problems with Doll's theorem. We want this to be highly connected because this is our configuration space and we needed that in Doll's theorem. And we need this to have a large independent set so that we can find these disjoint faces that we were looking for. And you can think of this as, as having two rabbits running in different directions when you try to construct sigma. On one side, you want the large independent set to extract the faces you wanted. In the other side, you want it to be highly connected so that you can use those there. And if I want to, so think a bit about how you would force a simplicial complex to be highly connected. I would add faces to it to block the holes that it might have before. If I wanted to have a large independent set, I would have to remove faces so that I get my independent set. If you have an action of a group on it, then this just makes it a bit worse because every time you add a face, you have to add the whole orbit of that face. Every time you remove a face, you have to remove the whole orbit. So you have these two conflicting things you want to be doing, and we want to sort of find a simplicial complex that hits the sweet spot for our theorem. So let's just review a bit how large do we want the independent set. We wanted to have Q vertices. This is precisely so that we can find our Q faces which were pairwise disjoint. And how connected do we want this? We want it to be at least this connected. So P over Q, we can leave out a constant, minus a constant connected, okay? And this is what was difficult in our proof, finding a simplicial complex that satisfies these two things. This is sort of on the nose about how good you could get things to be, because if you could do things significantly better than this, you could reverse engineer this this method to get Tverberg type theorems that we know cannot hold because of the lower bounds we have, okay? So if you have something that's roughly this connected, you shouldn't be expecting to have Q plus 1 vertices, an independent set of with Q plus 1 vertices here. Okay, maybe why this actually works. So if you try to run this through the machinery I told you about, you have this configuration space here. Now the map goes to or P times D plus 1 because you have P faces you were constructing. So those are the big two changes. And if I want to apply Stoll's theorem, I want the dimension here. So if I don't run into a problem, the dimension here should be bigger than the connectedness here. The connectedness on this side should be this much if this was the connectedness of sigma. And the dimension on this side is precisely this. And now just divide by P. So it gives you this thing. And then take P to infinity, okay? So as P goes to infinity, the inequality you have to not run into problems is precisely this one. And you multiply by Q, you get this. So if n is bigger than this number, this machinery should tell me that I have this Tverberg data. So this seems that if I had one more point than what I promised you, this should work nicely, okay? Okay, so this proves the theorem if we have one more point. So before I go on to fixing this, let me tell you about how you construct this simplicial complex. And the idea is to think of P points arranged on a circle. And what I'm going to do is any subset of them is going to be a face if any two of them are a distance at least Q on the circle. So for any of this, I count q minus 1 on the right and q minus 1 on the left, and I'm not allowed to use those. These are like the simplicial complex of points which are socially distancing on the circle, okay? And so this guarantees that I have my independent sets which are large because I just take q consecutive points of the circle and they form an independent set. The problem is dealing with the connectedness of this. So gaps have at least q minus 1 vertices, and the problem is that this is not connected enough. The reason you might have this problem is, imagine that we have to queue on a line, and I have to stand at least 6 feet behind the next person, okay? So if I stand 6 feet behind the next person, that's perfectly fine. If I stand 12 feet behind the next person, then someone can take my place and get in the middle between us two. But if I stand 11 feet behind the next person, then there's not enough space for someone to go between us, and so the next person should really go behind, okay? So whether you think that standing 11 feet behind the next person is me being clever or obnoxious, it's a completely different story, but this sort of thing could happen here. You could have points which are roughly 2q minus 1 vertices away from each other, and it would give you maximal faces. You have maximal faces of dimension roughly this much. And this really creates problem in homology for the connectedness of your set, okay? So what we have to do is remove these low dimensional faces. I think of it as having a nice statue or simplicial complex that you have here, and you have a bunch of spider webs which are low dimensional. You don't really want them, and you just have to get rid of them to get to the simplex that you wanted. So the idea is to take faces of dimension roughly p over q, which was how connected I wanted things to be, and their subsets, and see if that's connected enough. Okay, and that's actually what works. So this allows us to prove the topological Tverberg theorem with this many vertices, and this plus 1, we get rid of it by a final application of the German trick that I told you about there. But it's just another nice thing that p is a prime number, so get it this way. So in the last couple minutes I have, let me just tell you a bit here. So CAP is a subset of the number from 1 to p that can be extended to a face with at least a vertices as a cyclic thing that I was telling you about, and LAP just for those where my points are on a line, and I want my gaps to have the size I told you before, but I also want my faces to be able to extend them to have at least a vertices. Okay. So for example, for C39, have 9 points here. I basically only have a face that looks this way, this one and this one, so I get CAAQ to be the union of a disjoint simplices, so it's very disconnected. If I give you one more vertex, and I want to do the same thing here, so I have faces like this, but I also have this face, right? Here my gaps have at least 2 points, so I get a bit of slack to move things around. And I can start moving things around here. So this turns out to be a triangulation of a bundle over a disk. And so this is connected, but not simply connected. So as the number here below starts growing, how connected your simplicial complex is actually grows. And so the big theorem is that once you get to this number, you get to a high connectedness, and the result basically holds. So I had some slides about how this actually glues together a bit, but the main thing is you start breaking down these complexes, and you want to prove by Mayer-Vittorius that they get to be as connected as you wanted. The linear sets I told you about, they are either empty or highly connected that you can prove by induction, and those appear often in the cyclic one. Because if I look at the faces that contain this point, the other vertices, they have to be here. So I have p minus 2q plus 1 vertices available, and I really get the linear complex here if I remove this vertex. So you get a bunch of complexes that look this way, glued together in a nice way, and you have to check that they they actually work nice. So the final thing is, as I told you about, a final application of the geometric to get to the exact number we wanted, and that's the moral of the story. So instead of assigning single labels, you assign faces of sigma to each vertex, and you get a result of this type. So this is as far as I wanted to get to today, and yeah, thank you for the invitation.
Thank you. It was great. But I have actually, to be honest, I didn't quite get how you delete the faces. So I mean, the construction of your complex is clear. I mean, it's everything.
So,
And then some kind of magic for me. Yeah.
so
This step, yeah.
Think of this complex where the gaps have to have size q minus 1. And fix a number a that you want. And take all the faces that have dimension at least a and their subsets.
Yes, at least a.
Yeah, that's the complex I want.
Mm-hmm.
So the low dimensional maximal faces, those get removed. If some of their complex was, if some of their subset was also a subset of a high dimensional face, we keep those.
Still, it's not clear how. I mean, it shall remain complex, yes. So.
Yeah. So for you want it to be closed under subsets, right?
Yes.
So you take a particular family of maximal faces, which are those which are high dimensional enough, and their subsets.
Okay.
So that makes it closed under taking subsets, and that gets rid of the maximal faces I really didn't want. And fortunately, it actually has the, once you go through the murky details of seeing how connected it is as connected as you want it to.
Okay. Okay. Any other questions?
Thanks for a lovely talk, Pablo.